So this chapter is about internal forces. Now remember, in the previous chapters we were discussing about action forces and reaction forces. Now action forces are those forces which are being applied on a structural member. For example, if there is a wall and I'm trying to push the wall, so this push is actually an action force. Now the wall should move, but the wall is not moving because the wall is applying an equal and opposite reaction forces. Now these reaction forces gonna cancel out and the wall will not move. Now in addition to these action and reaction forces, there are another set of forces which are called internal forces. Now internal forces are important because internal forces helps to a material. We need a material, that material will resist those internal forces. So in order to design those structural systems, we need to identify how many internal forces are acting on this structural system. So this chapter is divided into three main sections. In section 1, we're going to discuss these internal loadings, internal forces which are developed in the structural member. And these internal forces are basically divided into three main categories: normal force, shear force, and moment. So we will understand these shear and moment equations, and also will draw these shear and moment diagrams. And finally, in the third section, we will discuss a relationship between the distributed loads and shear and moments. Okay, so why we need to consider these internal loadings. In design, when we are designing these structural members, it is necessary to know the loading acting within the member to be sure that the material can resist these loads. So in order to design these structural members and in order to make sure that these materials which we are using to design these structural members can resist the loadings, we need to identify how many loadings are being applied on this structural member. So that's why we are interested in understanding the internal loadings. For example, let's just take an example of this structural member. This is a cantilever beam which is having a fixed support, and now there are two loads being applied on it. So these loads are actually the action forces. So P1 is one action force, P2 is another action force. Now, as a result of these action force, we will have reaction forces at the support. So let me draw this beam here, and this is a fixed support, and this cantilever beam is being applied by these two loads, P1 and P2, and as a result of these loads, we will have reactions. And we know that at the fixed support, we have three reactions. One is normal force, another is one is acting on horizontal axis, and one is acting on the vertical axis, and the moment. So these are the reaction forces as a result of those actions. But now in addition to these action and reaction forces, we also have internal forces which are transferring these action forces into these reaction forces. So in order to find these internal forces, we can use the method of section which we discussed in the last chapter. So in this method of section, what we have to do is that you can just take a section and you can expose these internal forces. So if I will take this beam as an example, I will just cut somewhere here, and as a result I will expose these internal loadings. So internal loadings are basically of three types. One is a normal force, another is a shear force, and another is bending moment. So you can see this example as here. So these are basically the reaction forces, but these are the internal forces. Now you have three types of internal forces. VB would be shear force, NB is normal force, and MB is bending moment. So these are the three types of internal forces which we usually see in a 2D structural members. Now if we look into 3D structural members, we can also identify these forces. Now later I'm going to explain what these forces are defined, how these forces are defined, but for now the force, this one is called normal force, and the force acting downwards is called shear force, and in addition we have a bending moment. So if you look into a three-dimensional member, so you can see that there is one force which is a normal force, and then along the plane you have shear forces Vx and Vz, and also you have two bending moments Mx and My. And in three-dimensional members, instead of like in addition to these normal and shear forces, you also have a torsional moment. But this chapter we will just discuss about 2D structural members, in which include shear force, normal force, and bending moment. So what is a normal force? Now, the force component that acts perpendicular to the cross section is termed as a normal force. For example, in this case, this force element is acting perpendicular. So this was a beam section, and this is a force which is acting perpendicular to the cross section, which we expose to extract these shear force, normal force, and bending moment. So the force which is acting perpendicular is called normal force. Now the second force is shear force. Now this shear force component is tangent to the cross section. Now if you see a shear force, this is tangent to the component, so this type of force would be called shear force. Now the third type is called bending moment. Now this is a force component that is producing a turning effect of a force. Now previously also we studied this bending moment, so we will also have this bending moment because it's a structural member. Now it is also important to understand these sign conventions, because previously we studied sign convention for action and reaction forces. Remember in the last chapter we were doing a lot of examples in which we were taking summation of f of x is equal to 0, summation of f of y is equal to 0, and we were also doing summation of moment is equal to 0. Now these, we considered all the forces acting on right side to be positive, and for f of y we took all the forces that were acting on the upward direction to be positive, and for moment we considered all the moments that are acting anti-clockwise to be positive. Similarly, we also need the sign convention for internal loadings. So these are the three sign conventions which are followed conventionally using for the internal loadings. Now let us discuss first the normal force. Now the normal force is said to be positive if it creates tension. So if the force is creating tension, then this type of normal force would be considered positive. For example, this is a member, let's just say it's again a fixed support, and this is a structural member cantilever beam which we were discussing in the previous slides. Now if a force is acting normal and this force is kind of creating tension, so if it's creating tension, then this type of force would be considered positive. And if it would have been acting in the opposite direction, then the normal force would have been negative. Similarly for shear is considered positive if it causes the beam segment to rotate clockwise. Now what do I mean by this? For example, again, this is a cantilever beam, and for this cantilever beam, if we expose this, for example, we have exposed the internal forces, so we cut down, took the segment and exposed the forces, so you have a shear force which is acting downward, and in this case, because it's the other side, so we'll change the direction. So in this case the force is acting upward. So since it's making, if we try to do this, it's making this structural member to rotate clockwise, and similarly in this case also it's acting on a structural member and trying to rotate it clockwise. So this clockwise rotation, it means that these directions are considered to be positive. Now, when we will do the example, we'll understand these more clearly, that how these sign conventions work. But for now, we just have to remember that for normal force, if it's creating tension, it's positive. If it's creating compression, it's negative. And for shear, if it's applying on a beam such that it's trying to rotate it clockwise, so clockwise shear is positive and anti-clockwise shear is negative. What about internal bending moment? So internal bending moment is positive if it will tend to bend the segment in a concave upward manner. So what do I mean by this? For example, again, I will draw a beam and I will expose the internal loadings, and let's just only talk about moment for instance. And this moment is tending to rotate the cantilever beam in a concave upward manner. So if we will imagine how this bending moment will rotate the beam, so it will rotate the beam something like this. So this is a concave upward manner. So if a bending moment, if we will assign some direction on a bending moment, and that bending moment will try to make this beam bend in a concave upward manner, then this kind of bending moment would be considered positive. Now, when we will do this example in the next slide, then it will become more clear how this all works. But for now, just again, we'll do this one more time and then we'll move towards the example. So for normal force, it is positive if it creates a tension. For shear, it's positive if it rotate the beam or a structural member in a clockwise. And for bending moment, it's positive if it will bend the structural member in a concave upward manner. Okay. So let us do this example. So now this example says that we have to figure out the internal forces at point B and at point C. So before calculating the internal forces, let's just try to use this method of section which we discussed in the last lecture to figure out these internal forces at point B and C. Now before doing the method of section, first we have to find the reaction forces. Now this joint A is a roller support. So this roller support has one reaction vertically. I will call this AY. And this is a pin support. So pin support has two reactions. I will put this and I will put this, and this is D of Y and this is D of X. Now in order to find the external forces, now these are reaction forces, we will apply equilibrium condition, which is summation of f of x is equal to 0. And in finding the external actions and reaction forces, we take the sign convention that all the forces that are acting on a horizontal direction are positive. So if we will do this, there are no forces which are acting along horizontal x-axis, just the d of x. So d of x is 0. Now we can apply summation of forces along y-axis is equal to 0, but in that case we will have two unknowns. So let us just try to do summation of moments at D. So if we will apply summation of moments at point D, and the sign convention was that anti-clockwise is positive. So if we do summation of moment at point D is equal to 0, then the force AY is clockwise, so it would be negative, and we have 6 plus 3, the moment arm. And then we have another force 6 which is anti-clockwise, so it would be positive. So, and the distance is 6. And we have an anti-clockwise moment also, which is 9 kilonewton meter. And we don't have anything else, so it would be 0. So if we do the math, we will get AY is equal to 5 kilonewton. So this is our AY. Now we can calculate the dy, and we can calculate it simply because it is 6 kilonewton, and we know AY is 5 kilonewton, so it also has to be equal to 6, so it would be 1. But let's just try to find first. So summation of F of Y is equal to 0, and the convention is that all the forces acting on our direction are positive. So AY would be 5 kilonewton positive minus 6 kilonewton because it's acting downward, plus dy, which is acting upward, is equal to 0. So this would give us dy is equal to 1 kilonewton. So we have all the forces. Now it's time to find out what are the internal forces. Now internal forces are different at different points. So in this example, we'll try to find the internal forces at point B and at point C. So let us first try to find the internal force at point B. So for that, we have to actually extract. We have to make a section and expose the internal forces. Now let us do that. So this is a beam and this is a roller support, and we have reaction force which is 5 kilonewton. And since we are cutting at point B, so we will not include this 6 kilonewton force because it is acting after the point B, and the distance is 3 meters. And when we expose these forces, we have a normal force, we have a shear force, and we have a bending moment. And remember, I'm considering all these conventions as positive. So according to the sign convention we studied before, this is normal force. I will call it N, and this normal force is positive because it is creating tension in the structural member. And this is a shear force, and this shear force is also positive because it's rotating the beam clockwise. So this is also a positive convention. And the bending moment is, if you see how this bending moment is bending this beam, so it's trying to make it a concave upward. So if you will see how this moment is bending the beam, so it is bending the beam like this, concave up. So this is also a positive convention as far as the internal loadings are considered. Now we have exposed the internal loadings. Now what we will do is that we will try to find what are these internal loadings. So again, we will apply the equilibrium equation conditions, which is summation of f of x is equal to 0. And in that case, we will just directly get n is equal to 0 because there is no other force acting on a horizontal direction. And when we will apply loadings in vertical direction, all the summation of all the forces along y-axis is equal to 0. So we have 5 kilonewton force acting upward, and the only force that is acting downward is shear. So we get V equal to 5 kilonewton. So shear is 5 kilonewton. Now we can take the moments. So let's just take the moment which is anti-clockwise to be positive. Summation of moment at point B is equal to 0. So you have 5 multiplied by 3, which is the moment arm, and then shear force will become 0. Normal force is already 0. So you have anti-clockwise moment, which is positive, is equal to 0. So the moment you will now, this force is actually clockwise 5. So clockwise is negative. So moment will come out to be 15 kilonewton meter. So these are the internal forces. Shear force is 5 kilonewton, bending moment is 15 kilonewton meter. Now if we want to do the same thing and we want to expose the internal forces after 6 kilonewton applied force at point C, so how that would come out to be. So in that case, we have to draw this free body diagram again, and the distance is same 3 meter, but we have an action force 6 kilonewton acting on it, and because of this we will have a reaction force 5 kilonewton, and we will have internal forces which we need to determine in this example. Now again we can do the same thing. We can apply summation of all the forces is equal to 0, and that would automatically give us n is equal to 0. And if we do summation of all the forces on y is equal to 0, so you can see it's 5 minus 6 and minus v is equal to 0. So you will come out to be shear is equal to negative 1 kilonewton. And if we want to calculate moments, we'll calculate summation of moments at point B is equal to 0. This is, oh sorry, it's C is equal to 0. So if we will do this, we will get 5 into 3, and all the other forces are 0. So we will get moments is equal to 15 kilonewton meter. So that's how you calculate. So you can see that before applying the force at point B, our shear was 5 kilonewton, and after this 6 kilonewton right after, we get shear force minus 1. So that's how you calculate the internal loadings, and with the help of internal loadings you can see like how the material is capable of resisting those internal loadings or not. Okay, so in design, a detailed knowledge of these variations of the internal shear force and bending moment is required. So for example, if you want to design this structural member, you need to know the internal forces everywhere, here also, or along all the beam, because the method of section helps us to find the internal forces at any point. But what we are interested in is to calculate the shear force and bending moment on all the points, because we want to design the structural member, and in order to design structural members we need to know what are the variations of the shear force, what are the variation of the bending moment and the normal forces. Now these figures helps us to understand. So these are the results of variation of shear force. So if we take different sections along the way and then calculate the values of shear force at every point, then this will give us a shear force diagram. Similarly, we keep on cutting the sections at different points and then extract the moments, so we will get the values of moment at different cross sections, and this type of figure is called a bending moment diagram. So it's very important in design that we extract these shear force and bending moment diagrams, and only after extracting these diagrams we can know where the shear is largest. So we can see that here we have the largest amount of shear force, so we need to put some material accordingly to resist that shear force. Similarly, we have largest bending at point B, so we need to design the structural members accordingly. Now there's another way in addition to this method of section to draw these shear force and bending moment diagrams. Now before we were taking a section and then we will calculating the internal forces, now what we can do is that instead of, we'll make a section, but instead of directly calculating shear force or bending moment diagrams, we can calculate by using equations. So we can formulate equations to calculate these shear force and bending moment diagrams. Now we will do one example to see how we can do this and how we can calculate these equations. Now for example, this is a beam, and let's assume that these are roller supports. So the first step is always calculate the reaction forces. Now these reaction forces are actually simple in this case, because you have a 5 kilonewton of load and the distance is 2 meter, and here also distance is 2 meter. So if you will calculate the vertical forces, it's gonna come out to be 2.5 kilonewton, and 2.5 kilonewton. So these are the internal these are the reactions which we calculated from the equilibrium equations. Now, in order to calculate the equations to draw shear force and bending moment diagram, what we can do is that we can make a section out of it. So if you cut a section like we did it before, so you can expose the internal forces. So let's just say this is point B, and at point B we don't have this 5 kilonewton because we cut a section just before the point B. So you have a reaction force which is 2.5 kilonewton, and you have internal forces which are normal force, shear force, and bending moment. Now we can directly calculate this, but what we are interested in here is to make an equation. So how we'll make an equation? We'll assume, because we are interested in distances, we are interested to calculate the shear force and bending moment diagram at different distances. So we want an equation where we can input the distance and we can calculate the shear force and bending moment diagram. So for that purpose, we need to have this distance as a variable. So instead of putting just some value, I will put a variable name. Let's just say this is x, and then I can calculate the this internal forces by applying equilibrium equations. So let's just try to do this. So if we will apply the equilibrium equation, that is summation of all the forces along y-axis is equal to 0, so you will get 2.5 minus v, so is equal to 0. So you will get v is equal to 2.5 kilonewton. So that's one answer. And if you will apply summation of moment is equal to 0, then at point B, so summation of moment at point B would be 2.5 multiplied by x, because now we have x, and since it's clockwise, so I will put minus sign, plus moment is equal to 0. So our moment at point B would come out to be 2.5x. So now you can put the value of x, and then you can calculate what is the moment at point x. But it is only applicable till you have a continuity of the forces. I will explain this later and it will become more clear. But for now, you can see that from here to here, there is a continuity. There is no abrupt change in the force actions. But after this, you have a 5 kilonewton of force, and now these equations will not be valid. So these equations are only valid if x is less than equal to 2 meter, because after 2 meter you have a change in force, and greater than or equal to 0. So if that's the condition, if x is between 0 and 2, then you can use these two equations to solve your internal force problem. Now, what about after 2 meter? So you have to repeat the procedure the same way. Take a section and then expose the internal forces, and after you expose the internal forces, you can calculate the internal forces by applying equilibrium equations. So this is what we're gonna do here. So let's just say I'm gonna expose the section from here. So I have a reaction force which is 2.5 kilonewton, and this is a point B, and I have an action force which is 5 kilonewton, and now I will assume x from here to here, and this is the value x, and the internal forces are exposed accordingly, and this is the force N, this is shear force, and this is bending moment. Now again we will apply equilibrium equations. So if we will do summation of f of y is equal to 0, you can see that you have 2.5 kilonewton, and then you have minus 5 kilonewton, and you have minus v, which is a shear force. So if you solve this, you will get your value as minus 2.5 kilonewton. Okay, so if you do summation of moment at this point is equal to 0, so you have one force, two force, so you have two forces. So this is a clockwise, so it would be minus 2.5 into, what is the distance? The distance is x. And then you have this force which is anti-clockwise, so it would be positive 5 into x minus this distance. So this distance is 2 is equal, and you have another moment which is m is equal to 0. So if you solve this, you will get the value of moment as 10 minus 2.5 x. So this is the equation, and these two equations, equation 3 and equation 4, they are only valid if x is greater than equal to 2 and less than equal to 4, because from here to here there is no change in the action forces. Now we have the equations. Now we can draw the shear force and bending moment diagrams. So let us draw shear force diagram here. So this is our same beam, and let me define the distances. So this is 0, this is 1, this is 2, this is 3, and this is 4, and the force is acting on point 2. So let me explain this here. So you have this distance, this distance, this distance. So this is distance 1 meter, this is 2 meter, here we have 3 meter, and here we have 4 meter. So all you have to do is apply these equations and calculate the shear force. So the shear force is 2.5, so there is no x. So if it's 0, you're gonna get 2.5, 1, 2.5, 2, 2.5. So whatever x is, the shear force is gonna remain same, which is 2.5 meter. But after this 2, we have to use this equation, because this equation is valid after 2 meter, and it's again minus 2.5 here also, here also, here also. So this is minus 2.5. So if you join the blocks, so this is a shear force diagram. So you can see that you have positive shear in the first half of the beam and negative shear of 2.5 kilonewton in the second half. Now what about bending moment? So let's just try to extract the values for bending moments at each point. So the bending moment is 2.5x. So if x is 1, our bending moment for 1 would be 2.5. So if x is 0, then our bending moment is 0. When x is 2, so 2.5 multiplied by 2, our bending moment is 5. So let's just draw. You have 0 here, you have 2.5 here, you have 5 here. So it's a triangle. You have 0 here, 2.5 here, and 5 here. So to calculate at distance 3, you need to use this equation. So if you put 3 here, it would be 7.5, and 7.5 multiplied by 10, it is 2.5. And if you put distance, so it's gonna be 2.5. If you put distance 4 here, so 4 multiplied by 2.5 would be 10, 10 minus 10 would be 0, so it's 0. So this is 2.5, this is 0, and this is 5. So that's how you calculate the shear force and bending moment diagram. If I draw it here, this is the shear force diagram with 2.5 here and 2.5 here. And if I draw a bending moment diagram, it's something like this. You have 5 kilonewton meter at the center, and then you have 2.5 here and 0, 0 here. So that's how you can calculate the internal forces if you want to draw shear force and bending moment diagrams. Okay, so sometimes this method also gets complicated, because imagine if a beam is subjected to several concentrated forces, couple moments, and distributed loads, then this method of constructing shear force and bending moment diagram become quite tedious. So in order to solve this, we have simpler methods to calculate internal force diagrams, and we can utilize differential relations between load, shear, and bending moments to draw this. So what I mean to say is that imagine you have this type of loading condition. You have two concentrated forces, you have a distributed load. So it gets very complicated to do the method of sections and calculate the equations, because then you have to cut section here also, then here also, and here also. And if there are sometimes situations even complicated than this. So there's an easier method which utilizes these differential relationships, which we're going to explore here. And if you know these differential relationships, then you can calculate the shear force and bending moment and load diagrams very easily, the normal force diagrams. Okay, so let's try to understand. So for this, you just have to extract one portion, and I'm just gonna go through this, and it's not really, I mean, if you don't understand, then also it's fine, because later we're gonna just extract the solutions, and we're gonna use these solutions to solve our problems. But for now, I'm just gonna explain the math behind it. So in order to calculate the relationship between the distributed load and shear, we just have to extract one part out of it. So let's just say this is the part which we are gonna extract, and this part has a distance x from the support, and this part is part of the distance. Then I would represent this as delta x. So this is that component which we have extracted, and from this component we will try to develop these relationship between the distributed loads and shear. So after extracting this part, we can expose the internal forces. So these are the internal shear forces acting on it, and this is the internal bending moment acting on it. So we can see that here we have shear force M, bending moment M, and shear force V. And opposite, we will have shear force V plus delta V, because as we move from X to delta X, we will have loadings. Before it was W, and now this loading will also increase. So we add V plus delta V. Similarly, we'll have a additional moment also as we move from left to right. So you have to develop these equations which will help us with these differential relationships. So we're gonna explore these relationships. So how we can do this? We can use the equilibrium equations to solve this problem. So let's just apply equilibrium equation. So let's just say I'm gonna apply summation of f of y is equal to 0. So if I apply summation of y, so how many forces are acting on vertical direction? We have a shear force V, and then we have these distributed loadings, because distributed loadings also act on vertical direction. But distributed loading can be calculated from this formula, because previously we were just considering one force. But if you have a distributed loadings, multiple forces, so you need to calculate the resultant of that force, and the resultant of that force would be multiplication of this distance with this force. So let's just say we have a force Wx, and the distance is delta x. So the resultant force would be this distributed loading multiplied by the distance. So this is what we have here, and I'm gonna put this resultant force, which is Wx, into delta x, and we have another force, vertical force, this one. So it's V plus delta V is equal to 0. So I can solve this, but if you solve this equation, you will get delta V is equal to Wx delta x. So no need to understand all this if it seems a bit complicated, but I'm just gonna get to the answer, and then I'm gonna explore that what these mathematical formulation would actually mean. So what I want to calculate here is that I want to calculate the relationships between these distributed load and shear, and I want to explain that what does that mean and how we can use these relationship to just directly draw shear force and bending moment diagram. So that's the idea. Ultimately, by the end of this formulations, we should be able to just directly draw shear force and bending moment diagram instead of doing the method of sections. So delta V would be Wx delta x. So if I calculate this, Wx is delta V by delta x. So what does that mean? This delta can be transformed to differential values if we assume that this delta x approaches to 0. So then it would be Wx would be equal to dV by dx. And if we integrate this, so we can calculate the change in shear, which is equal to Wx dx. So what I mean by this is that you can calculate shear if you have the loading condition and if you know the distance between them. So if you take an integral of loadings, then that integral of loading is called shear. Now once we will do the example, then it will become more clear. So the final result which you need to remember is this one. So this is a slope of shear. So slope of shear is equal to distributed load intensity. So if we have this distributed load, we can calculate the slope of shear diagram. And similarly, if we have loadings, so we can integrate the loadings and we can calculate this shear force. Now what do I mean by this? I will explain when we will do the example. Similarly, we can calculate the moment if we know the shear. So we can take the integral of shear and we can calculate the moment. Now that was in the case of distributed loadings. So if we don't have a distributed loadings, we have just this one force or one moment, then our force is just equal to the shear and our moment is just equal to the moment. Now, okay, so let's do one example, and in this example, we will not use method of section, but we will directly calculate the internal forces by the method which I explained in the couple of these slides. But we don't have to remember all this and we don't have to keep in mind all the formulations. We just can use the results, which is that from these loading conditions, we can directly calculate the shear force, and once we have the shear force, we can directly calculate the bending moments. Okay, so this is our example. We have a beam, and this beam has this distributed loads of 1.5 kilonewton per meter, and then it also has this concentrated force of 2 kilonewton, and we have a bending moment of 11 kilonewton meter. So now we have these loadings, and from these loadings we're going to extract the shear force diagram. So how to do this? So as explained in the couple of slides, we just have to take the integration of these loadings, and by integration we'll get the shear force. Now integration means that I just have to keep on adding whatever the loadings I'm getting, and by doing this we will determine the shear force. So let's just try to do this. So this is a beam and it has an external load 2 kilonewton and a distributed load 1.5 kilonewton per meter. So how to draw a shear force diagram? So let's just draw a shear force diagram. So we just have to keep on adding the forces. Now first we'll start from here, and since we are starting from here, it's at very beginning we have a load of 2 kilonewton which is acting downward. So we're gonna just make this load and add it to the shear force. Now from here to here we have no load and the distance is 2 meters, but we have no load. So we're gonna not add anything, not gonna subtract anything, and we're just gonna move forward. From here it says that the next 2 meters you have 1.5 kilonewton per meter of distributed loading. So it means that at every meter I have to add 1.5 kilonewton, because 1.5 kilonewton is acting on every meter. So if I go 1 meter forward, this was 2 meters, and this is 1 meter, and this is 1 meter, and you can see this from here. So if I go 1 meter, I have to add 1.5 newton of force. So I add 1.5 newton of force, so it is now 3.5 kilo Newton. And if I move 1 meter again, I have to add 1.5 Newton of force again, so it will become 5 kilo Newton. So that's how you draw a shear force diagram. So before, the equations we were trying to formulate resulted in these relationships. So if you have a loading condition, you just keep on taking the integral of those loading conditions and you can get the shear force diagram. So you can also draw bending moment diagram in a similar way, but bending moment diagram can be formulated by taking an integral of shear force diagram. So we have a shear force diagram now, and we're going to take the integral of shear force diagrams to calculate the bending moment. So how we have to calculate the integral is, you have shear force which is 2, but at that point, at the start, you have distance 0. So 2 multiplied by 0, you would be getting a 0. And if we go to distance 1 meter, so 2 kilonewton multiplied by 2, you will get 2. So you have a 2 kilonewton meter. So if we talk about this, I'm going to change the color. So here you just have to take the integral, which is also area under the curve, which is 2 multiplied by 2, 4. So you have here, you have a bending moment of 4 kilonewton meter. Now what is the area of this thing? We can calculate the area of this thing by dividing into two parts. So this part is 2 multiplied by 2, which is 4, and this part is 1 by 2 into this distance into this distance. So this distance is 2 meters, and this distance is 5 minus 2, which is 3. So if you add this part with this part, you will get 11. So this is 11 kilonewton meter. So that's how you can calculate the bending moment diagram. So in this lecture, we have investigated method of section to calculate the internal force diagrams, and after that we developed equations, and after developing equations we investigated these relationships between loading condition and shear force diagram and bending moment diagram to calculate these shear force and bending moment diagrams. So this is chapter 7, and see you in the next chapter.